right, Styon. Styon is a pretty new company, a couple years old. We were a spin-off from Dow Chemical. It's the styrene envelope that Dow packaged up, styrene, butadiene, latex, rubber products of various sorts, polystyrene, polycarbonates, and compounds and blends. And it's about $5 or $6 billion of business. It's now owned by Bain Capital. We're a private company. We have 2,100 employees globally, 25 countries, 67 manufacturing plants. That number varies a little bit. 20 manufacturing sites around the world, all the continents, and really a leader in our key market segments. So, Larry talked about migration. We have a unique situation. We have a totally uniform control system, a proprietary system. Most of you know Dow had they call it Mod 5, and it's in all of our plants. We have to migrate these by 2020, and that's an agreement we have with Dow. So we can take a very structured, disciplined approach to this migration from a corporate level. I'm going to use my clicker here. These plants are highly automated, so there's an incredible amount of instrumentation in these plants. Half of them are batch, half of them are continuous. In Dow, the philosophy was total automation. MOD stands for Manufacturing Operating Discipline. So as a result, even though they're very old systems, they're very capable. And they have all this state-based automation procedures built into the code. So it's not just loop control. We talk about driverless cars and Google and all of this stuff. Well, guess what? Dow has driverless plants. Basically, the operators monitor the plants for abnormal situations, shutdown alarms, emergency alarms. But the plants push a button, they start up, they run, push another button, they shut down. And we have various levels of sophistication in those procedures. As a result of embedding all of that procedural automation into the controllers, we can reduce staff in terms of operators per shift. We have very good safe operation because the knowledge of how to prevent process safety incidents is, as much as possible, is built into those procedures, et cetera, et cetera. We also put a lot of asset utilization information into those procedures and into the code so that we can run at rates. We don't really rely on the operators to get these things really ramped up to high rates. Plus, you can layer even on top of all that, advanced control if you want. So the question is, how do we capture all of that embedded knowledge in the code and do these migrations and at the same time increase our capability? So we don't want to just port code over blindly. We want to take advantage of the new modern platforms, but still not lose what we've built into the code over the years. So it's a very large capital project that's going to span several years here. And in our peak, we'll have about 7 plants per year that we'll have to do. We can't afford schedule slippage because we've got a drop-dead date of 2020. And again, we don't want to miss out on functionality. So in my mind, it's like, what are the key factors for success during migration? I broke it up into 4 categories: process, methods, quality software, tools. So in terms of process, there's 3 processes that, let's call them work processes, that we want to be able to deliver this quality software from. First is kind of the feed agile work process where we take black boxes, or we want to uplift some of our procedures and our thinking, or how to apply the new platform, and that is a very intensive, expert-driven, agile-driven work process. Once we get those black boxes figured out and our strategy figured out, then it's just production. We've got to crank out these plants, 7 per year. So that's project implementation. Once the plant started up, and that plant's off the list and we're on to the next plant, the plant that just started up is going to have continuous improvement that needs to be done on that plant. So we want to be able to use the same work processes for each of those 3 levels of code generation, application, and maintenance. So what's the goal? The goal is quality software. We want to migrate our process technology. It's not just a code migration, it's a process technology migration. Because at the end of the day, it's about running your process. So in terms of quality software, we generate a functional spec, we generate the code, and then we test it. So part of quality software is tested code. And at the end of every project, we want to, and we've done this on past projects, obviously, but now in our migration program, we want to be doubly sure that we RCI and follow up on each of these projects in partnership with our control vendor so that we continually improve and drive the costs down. So I'm going to talk a little bit about methods. How do we drive this entire program in a rigorous way? I believe we really need to pay attention up front in a large migration program like this, where we're swapping out the brains of our plant for a new brain with vastly new capability, and think about architectural principles. And then I want to touch on the legacy to transform model. I don't have a lot of time to dwell on it, but maybe some of the other speakers can talk about it too, is in terms of physical and procedural models, we want to recategorize our physical model in terms of like an S88 model, but especially we want to capture that process knowledge and recategorize our procedural model. So there's 2 reconceptualizations of our process that we'll be doing: physical model and procedural model. In terms of that, we want to use off-the-shelf software. We want to use just commercial libraries. And we also want to focus on developing reusable libraries, which I call software product lines. And I coined that term, or borrow that term, from the Carnegie Mellon Software Engineering Institute. So to me, an SPL would be an equipment module library. So this is how to run a centrifuge. This is how to run a filter. This is how to run a pressurized recirc system. This is how to run a tank. This is how to run a truck offloading system, at least for our business. We package that up, we version control it, and stick it in the library. That's a software product line to me. The other key thing is tools. These are computers, extraordinary, powerful computers. SQL database, C++, C#, you got all these tools. We got young folks that know how to make these things dance and sing like a Stradivarius violin. So let's take advantage of that. Working with our vendor, we've built some tools that really help us drive this entire work process. The analysis, the design, the transformation, the functional specs, the configuration, and the maintenance process all will be driven with a set of computer-aided software engineering tools. And this is going to be driven out of the cloud, and we've heard that quite a few times already. So in terms of the steps, all these top 3 steps are driven out of the cloud. So identification, what's the scope? We put the definition requirements into the database. We flesh out those requirements into a design requirement and use the same database to help build the application. We also do application testing in the cloud. When we're ready, we can drive that application down to the plant level and do integrated test and approval there. For the first time, that would be like FAT and SAT, and then start it up in the plant. So this is kind of a modification of the ARC lifecycle model. So our thought is that whether we're doing a conversion or building a new plant or just maintaining the plant or adding to the plant a new train or something, we want to use the same work process for all of that. And use that for the life cycle of the plant, even when we're doing incremental improvement. And one day the plant shuts down, maybe. So architectural principles. I want to talk about some of these key principles. I like to use the terminology similarity principle. Every level's built the same as the level above and below. It needs to be single source, object-oriented and modular, and we want shared libraries, reuse, and version controlled. Extremely important. So let's talk about legacy to transform model. So what are we doing? Our legacy model is very flat. It does not contain relational data. It's proprietary structured text. There's no physical or procedural hierarchical models, and it's not object-oriented, so it's just structured text. Thousands and thousands of lines of code of structured text. So what do we got to do? These things are organized by sequence, and we've got the I/O list. So part of our migration strategy is to consider this a process technology migration project, not just code migration. We are reorganizing our physical and procedural models. And in essence, we're re-engineering a functional spec. So the key difference we're doing here is driving into this model the equipment layer. So we have our devices. We're adding into our library, or our software product library here, the equipment layer. That's really key. So we're bundling into that equipment layer the procedure for how to run that equipment and version controlling it and stick it in the library. Equipment tends to have, right, fixed procedure. The unit level, plant area, plant. This now can go batch or non-batch. We can layer batch on top of that or not. So here's our work process. We built a central database that contains all of our legacy functional specs and our transform functional specs. We take the legacy code out of the old controller. With case tools, we reverse engineer it into a functional spec. What I call 100% code accounting. So we know everything about the code, all the set points, all the code functions, all the alarms, all the interlocks, all the state-based automation, all the smart alarming, all the step transitions, we all capture that. And then re-engineer it using our tools into a new functional spec for the new system using the new libraries and the new software product lines. And we want to express this data in a transform functional spec and our legacy data in a legacy functional spec in the same terminology. So we could sit down with an operator and they could say, yes, this is how my process runs today. And then the new one, yes, this is how my process will run tomorrow. And we can use those same kind of data reports in reviews. So here's, we're talking about shortening product or project delivery lifecycle. In terms of, say, a pharma type project, the bulk of the cost of the project is more heavily weighted on the software side, validation, documentation, and software. In our businesses, it's about 50-50 because we've got so much automation in our code. Plus, we're going to be putting batch on a lot of our plants. So it's going to be more heavily weighted still for us to the application side versus the hardware side. So the software is going to cost more than the hardware. So we really want to shrink and drive the costs out, shrink the time cycle, and drive the costs out of delivering applications. So to do that, I'll just go through the cycle, right? So we have our functional spec. The automation engineer puts that in the database. And this spec can get read into the database automatically, or we can actually print out the functional spec automatically too. So we can work in both directions. These tools now contain all the decisions, conventions, and standards that we've decided on, which libraries to use, how to set them up, what options we expose. Everything's in that database. We therefore don't have to go code down in the DCS itself. We can create the DCS application from the database and get ready for simulation. Now here's another key thing. We package the simulation for each of our objects with the object. We use simple tieback, but we put some energy into the structured text so that it's really good, halfway decent simulation. And my motto is, I want these applications, if we make a major change to them, cut some objects out, put a new one in, clean up the ties between the objects, push the button, go, I want to be able to be simulating within 5 minutes. That's a stretch goal. Today we're not there yet, but essentially that's the idea. So then we can bring in our process experts. We want to be able to bring in, via the cloud, a technology expert from a tech center, a head operator from a plant, or an experienced operator, and do a live simulation and say, is this the way that we need to make this change? Yes, no, good. Oh, okay, we need to make a functional spec. Bang, the very next day we can have another session with the same set of people and really try to shrink that cycle. So this is all done in what I call rapid agile development, simulation, and testing in the cloud. So, expected results. These numbers are based on my experience, but I'll appeal to authority, and they're also slightly more conservative than the Software Engineering Institute numbers for when you roll out SPLs. So I believe we can indeed drive a factor of 10 out of our old traditional way of doing things, with the automation engineer taking a big pile of paper, functional spec, and putting the code in there, and then finally going to SAT and FAT and all that. In terms of version controlling these objects in the library, pre-tested, validated, we can reduce testing. So the quality of these applications is going to go way up. Some pretty sophisticated stuff in here. There's interlocks, there's all kinds of behaviors, startup, shutdown that you want to do when the equipment faults or trips. So all this kind of stuff we can predetermine, pre-qualify, and reduce testing when we go to the more advanced stage of the project. We're going to drive the cost of applications down, factor 5. I've already seen this over and over again, so on this migration program, I have no doubt that we'll achieve these numbers. Decrease time to make an application. Time is money. Same thing, at least a factor of 5. Restructuring the embedded process technology discipline is my last key message. It's not just a code migration program, it's a technology migration program, and we want to open up and enable our processes to do more in the future than they are today. So if we got batch on there, we can have state-based units that aren't batch, units that are batch, all in the same application, in the same plant. We can introduce new recipes, new products, new features very rapidly, and we've got a work process and an architecture that supports the entire thing. And that's it.